Hello, everyone, and welcome to the Mindscape podcast. I'm your host, Sean Carroll, and today is one of those episodes that brings you a guest who people have been hoping and expecting to get on the podcast for a long time. That would be Max Tegmark, cosmologist and physicist, professor at MIT. I've known Max for a long time. In addition to being a physicist, he's also one of the co-founders of the Foundational Questions Institute, which we talked a little bit about with its other co-founder, Anthony Aguirre, a few podcasts back, and also a co-founder of the Future of Life Institute, as well as a well-known author and public speaker. Max sort of made his bones, physics-wise, by studying the large-scale structure of the universe and the cosmic microwave background. He's worked with some of the largest and most important experimental projects as an analyst, as a theorist, taking the data from these projects and asking what we can learn about the universe. But his interests are very broad. He's worked in the foundations of quantum mechanics, and most recently, he's been interested in artificial intelligence. His most recent book is called Life 3.0, Being Human in the Age of Artificial Intelligence, and we will talk a little bit about his most recent work in creating artificial intelligence that acts like a physicist. But his previous book was called Our Mathematical Universe, and that put forward a theory of a very, very big multiverse, bigger multiverse than most cosmologists ever think about, one in which all mathematical structures are somehow real. So that'll be the focus of most of today's conversation, working up to from our universe to the multiverse, why you would think that, what it all means, the big cosmic questions that we like to dig our teeth into here at the Mindscape podcast. Remember, for those of you who don't know, there is a web page, preposterousuniverse.com/podcast, and there you can get show notes for all the episodes, including complete transcripts. You can also click on a link to go to Patreon and pledge money when every podcast comes out. The people who pledge money on Patreon get episodes without any ads in them, and once a month they get to ask questions that are answered in an Ask Me Anything episode. So it's a worthwhile way to spend your $1 per week on the Mindscape podcast. And whether or not you're a Patreon supporter, I'm always very grateful for all the nice comments, all the reviews, all the ways in which people have told me that they really enjoy the Mindscape podcast. So let's go. Max Tegmark, welcome to the Mindscape podcast.
Thank you. It's a pleasure to be here.
Now, of the many things you're known for, the multiverse is certainly one of them. I just wrote a book on quantum mechanics in many worlds, so one of the very first questions I get, I'm going to give to you. What is the multiverse? What is the relationship to many worlds? What do all these words really mean?
So before we start talking about other universes, let's be clear on what we mean by our universe. We don't mean all of space. When we, in astrophysics, say our universe, we actually just mean the spherical part of space from which light has had time to reach us so far during the 13.8 billion years since our Big Bang. And it's huge. It has 10 to the power 78 particles in it and huge numbers of galaxies, but certainly not infinite, right? And if you call that our universe or observable universe, and space goes on for beyond that, which is what the simplest theory of what created our Big Bang predicts, the inflation theory, then there are other universes just like it. I call that level one.
So, but other universes in that sense, it means more of the same, but further away out of contact with us.
Exactly. There just could be other people living on some galaxy 100 billion light years away. When they look around, they don't see us because light from us hasn't reached them. And someone might say, oh, that theory you have that Earth exists with Sean Carroll is just philosophical BS.
Unprovable, yeah.
But it's all part of the same space. And then, if you take seriously this inflation theory, the simplest versions of them actually predict that space isn't just big and much bigger than we can see, but actually infinite. And moreover, that the distribution of stuff in space started out kind of randomly from place to place, which means that no matter how unlikely it is that the particles would have started out in such a way that Sean Carroll and Max Tegmark would come along 13.8 billion years later and have this conversation, the probability isn't zero, right, since it happened. And that means if you roll the dice again an infinite number of times, it will happen again somewhere else. And you can even crudely estimate how far you have to go till you get to the nearest copy of this universe. It's about a googolplex meters, where a googolplex is one with a Google zeros, and a Google is one with 100 zeros after it. Sounds pretty crazy, but actually much less crazy than what you conclude if you take this inflation theory seriously, because it actually says that there are parts of this space, most likely, which aren't just really far away, so we can't get there. Where the laws of physics you would learn in school would be the same, but what would you learn in history class would be different, because basically the particles started out differently, so things happen differently. But where you might actually learn different things in physics class too. I call that the level 2 multiverse, and the way you might get convinced to take that seriously is if you both trust people like Alan Guth and Andre Linde, who say that this inflation thingy happened, and you also take seriously the idea that the laws of physics might have more than one solution for what a uniform space can look like. We know that's the case for water. It can be solid ice or liquid water or steam. String theorists say the space we live in might be like that too, except there might be more than 3 ways, maybe more than a Google ways it could be. But this is a pretty general phenomena in physics. If you have some complicated equations, they can have multiple solutions. And inflation is such a violent process that it doesn't just create a lot of space, but it really sort of jostles things around so violently that it's quite possible that it created not just lots of one solution for how space can be, but huge amounts of many different solutions. And we might be tricked into thinking that the solution that we live in is the only kind because it's all we ever see. But that would be just as dumb a conclusion as if some fish in the Caribbean concludes that all water is in liquid form because it's all it's seen. If it swam up to Greenland, they would see icebergs and realize that, hey, there's more. So that's the level 2 multiverse. It's more diverse.
Actually, maybe let me dwell on something about the level 1 multiverse, because I think it does get glossed over a little bit. Level 1 multiverse, let's just imagine space is infinite, right? The universe is open. And this is something that cosmologists have contemplated ever since we've been doing the expanding universe, right? And just from that one idea, it more or less follows that there's an infinite copy of people like you.
Almost, I would say. You could still have an idea which Newton and Einstein originally flirted with, that maybe space went on forever, like even Euclid thought 2,000 years ago. But there was only stuff in a small region of it. And then the rest was just this infinite void where nothing was happening. But inflation torpedoes that idea, because it says that actually all of the space is created with stuff in it. And it's also not just the same thing tiled over and over again, but it starts out kind of randomly in such a way that all initial conditions get realized somewhere. So I agree with you. If you put together these two ideas, infinite space and that you do all the possible initial conditions for them, then you're really forced into this conclusion that everything gets realized, which is quite shocking when you first contemplate it. And because long before if we travel into space, we get to that other conversation between Sean Carroll and Max Tegmark, a googolplex meters away, right? You get the other ones where you're interviewing Max Schmegmark and Max Pegmark about his golf playing and all sorts of other variations of our lives. And some people really don't like that.
And this is a conversation that could have been had in the 1920s, right? This is not like modern super duper crazy cosmology. Like the idea of an open infinite universe could have been taken more seriously decades ago.
And it was pretty violently attacked even before that. Anyone who listens to this, if you go to Rome, go to Campo dei Fiori, and there's a statue there of Giordano Bruno, who was burnt at the stake right there, the year 1600, for talking about an infinite universe with other solar systems and so on.
For doing a bunch of things, including that. There's historians who want to nitpick about exactly the reasons why his tongue was cut out and he was burned at the stake. But that was definitely one of them.
But I would argue that there are no scientific claims for which you should get burnt at the stake.
Okay, but good. So level 1 already has some weird philosophical implications in this many copies of me. Then level 2 is that there's also many different versions of the local laws of physics far away.
And just to add to that, I think it's important to remember that the things that we were taught to be laws of physics as fundamental the more we study them, we realize that a lot of those are actually not fundamental, but just more, that information is more like just part of your address, in the sense like if you have a T-shirt one day which has the theory of everything on it, which hopefully you, Sean, will discover one day, right? Would you expect to have a big 8 on there? And if I ask you, what's the 8 for? And you're like, well, 8, that's the number of planets in the solar system.
Yeah.
That would be pretty weird, right? Because you'll be like, Max, there are other solar systems out there too, with 2 planets, 5 planets. So the 8 isn't telling us anything fundamental about space. It's telling us something about our address in space.
Right. So we don't think that the average temperature of the air on Earth is a fundamental quantity of nature.
We don't.
Environmental.
We don't. But we did think for a long time that the number 1836 was kind of fundamental. That's how many times heavier the proton is than the electron, right?
Mm-hmm.
Oh, fundamental. And then a lot of our string theory friends tell us actually they have like a Google different solutions, and in one of them it's 1836. You can probably come up with another one where that number is 2019.
Yeah.
So maybe that's also just part of our address. In fact, there are so far 32 pure numbers that we've found, dimensionless numbers with decimals that seem to describe everything we, in theory, can try to predict about our world. Maybe they're all just part of our address also.
Yep. All right, good. We need a level 3 multiverse then, clearly.
Yeah, so this one comes not from studying the very big, what's out there in our physical space, but from studying very small things, the elementary particles they were all made out of. Where in the 1950s, this Princeton grad student, Hugh Everett, came up with this incredibly radical suggestion. Earlier, people had already realized that electrons, for example, and other subatomic particles seem to be schizophrenic in the sense that they can be in many places at once. And people had really bent over backwards to try to explain that away. For example, the Danish physicist Niels Bohr said basically there are certain questions you're not allowed to ask about nature. As a Swedish person, I am honor bound to always make fun of the Danes, and I think Hamlet was on to something when he said there's something rotten in the state of Denmark. But Everett said, no, that's BS. What's actually going on is, sure, these particles can be in several places at once, but that means that since we are made of those particles, we can also be in several places at once. And then instead of just freaking out and having a stiff drink, he continued thinking through what it would feel like if it really were that way. And he realized that if I make a measurement of a particle that's in 2 places at once, and in advance I've decided that if it's here, I'm going to go for a drink, and if it's in the other place, then I'm going to watch Netflix instead. What that's going to feel like is that there are going to be 2 different versions of Max now, and one has a drink, one watches Netflix, and they're going to be unaware of each other. And it's going to feel to them that there was just something random that happened. They discovered the particle was this way or that way, and then life went on. And we actually have known for many years that things seem to be kind of random in quantum physics. And he said that is the explanation. Everett said randomness is just the way it feels subjectively whenever you get cloned, so to speak. And people still argue fiercely about this, as you know.
I do know.
Over 100 years after quantum mechanics.
Know, yeah.
But I think it's important to realize that this weirdness is so fundamental. It has nothing to do necessarily even with quantum mechanics. Because if we just go across the river here to the MGH hospital, and they have a cloning device purely classically, where they just sedate you, and then they make an actual copy. They put all these atoms together in exactly the same pattern, and then you're told in advance that the next day, one of you is going to wake up in room 1, and the other copy is going to wake up in room 2. The next morning, both of the Seans wake up and they go out of the hospital room and look at the number on their door, right? What do you predict that you're going to experience? Do you predict that you're going to experience a 1 or a 2? What would you say?
I would say it's 50-50. I have an argument for this, but
It's going to feel random to you though, right?
Yes, exactly.
And there's nothing you can do to predict your subjective future experience, although the doctors would claim there was nothing random that actually happened. All they did was cloned you. So I think personally that Everett was onto something here. It's quite likely that yet again, our reality is really bigger than we thought, and that there is nothing truly random actually happening in nature, and the things that seem random come from us having been cloned in this sense. Ironically, even if this probably sounds even weirder than the level 1 and level 2, when you look at the kind of diversity you get in this, which I call the level 3 multiverse, it's actually smaller or no bigger than the other ones. It's just you get all the same parallel worlds sort of all over again in a different way.
You get them much faster in some sense. I mean, it's happening all the time in this room, right? The universe is just branching off into pieces.
And in some way you're also more connected to some of those parallel branches, because if you are upset that you got a parking ticket, you might realize that there's another you that actually was identical to you. It was up until maybe 10 minutes ago, and quite recently only branched out. So you can take more solace maybe in the fact that...
Does that make you feel better, really?
I think it takes the pressure off to get things right all the time.
It doesn't make me feel any different, but for better or for worse. But,
It does. I reflected a lot on this before my first son was born, and because I was hoping things were going to go well, and then I started thinking I have to try to align my emotions with my scientific views, because what do I even mean when I say I'm hoping?
Yeah.
If there are parallel universes where things are going to go great and things where they're going to end in tragedy, right? So then maybe I thought what I'm really hoping is I'm going to be in a parallel universe where things go well with this birth. But then I realized, no, that's stupid, because
that's
I'm
not a
going to be
good
in
way
all
of
of
thinking.
them.
Yeah, exactly. There'll be a version of you in all of them.
Maybe I mean that I hope I hope that in most universes it's going to go well. But that's also BS, because if you're really smart, that's just the number you could calculate from quantum mechanics, what fraction of the world goes well. So how can I hope for something, for some fraction being large? Just like saying I hope that pi is bigger than 3 or something. Either it is or it isn't.
But this is just a free will question. These would all be questions in a deterministic Newtonian universe, right? Where you just don't know what the future holds. Is there still the possibility of hope?
So I think in the end I ended up kind of where you are. It feels pretty cool to be in this universe, and sometimes it's useful to have little heuristics like hope, even if you know you're kind of on thin ice when you say things like that.
Hope comes from imperfect information.
Yeah.
Okay, so that's level 3. That's the Everettian multiple worlds of quantum mechanics. And that's separate from the level 2 cosmological multiverse, where things are different. And the typical speculative theoretical physicist stops at 3, but you will not be stopped. You're going to go on. You're going to say that there's a level 4.
That's right. So, of course, most people didn't even go to level 1. Giordano Bruno got burned, not just on the job market, but literally. That's become more normalized since now that we can see so far with our telescopes, and since inflation has caught on. Even level 2 has gotten a bit more normalized, moved from the ridiculed to taken seriously, albeit controversial. Even level 3, it's interesting to see how it's gone from being first utterly ignored to being violently attacked, to being actually regularly voted as one of the top interpretations if you talk to people who study quantum foundations. So it's sort of respectably controversial in the sense that people argue about it at conferences rather than just in bars.
Yeah.
Right. The level 4, on the other hand...
Sorry, before we get... Now you've raised a whole other issue that I got to get right. So I personally would put a greater probability on level 3 really existing than on level 2. I think that there's better reason to believe in the Everettian multiverse than there is in the cosmological multiverse. And maybe very roughly 95% for Everett and 50% for the cosmological multiverse. Do you have different credences yourself?
At the risk of being boring, I think I would agree with you on this, because there are fewer assumptions behind the Everettian one. Really, all you need is to assume minimalism. It's just the Schrödinger equation I have there in my office with no little footnote with ifs and buts, and this is not valid when someone observes, which we're not going to define for you. It's just the equation. Boom. Whereas to get the level 2 multiverse, you really need to assume both inflation and some fundamental theory that has multiple solutions, like string or loop quantum gravity. And neither of those two are things that we should be anywhere near 90% sure of at this point.
Okay, good. Just checking. All right, so we can get on to level 4 now.
Yeah, so level 4, this is extremely unpopular kind of multiverse, which
This is your chance to convince me. So
has very
here we
few
go.
people who take it seriously.
You have 100,000 listeners ready to be convinced.
Yeah, so the idea here is that so the way I got into this was first of all by just being fascinated by the effectiveness of mathematics in describing the physical world so well. And many people in the physics community, especially theorists like you, Sean, will say our universe is really accurately described by mathematics, approximated at least, or maybe it's even exactly described. But then you have to ask, what is the difference really between being perfectly described by math and just being math? After all, mathematicians, they also have this language of mathematics that they use to describe mathematical objects, like the cube, like the sphere, like some Calabi-Yau manifold, whatnot. And what modern mathematicians have increasingly done is try to strip out everything but just this brute formalism where they just describe different kinds of mathematical objects. You can make a type of mathematical family tree, which I had fun doing in my book, of all these different mathematical structures. Here are the integers, here are the real numbers, the complex numbers, here is quaternions, here is this 3 plus 1 dimensional pseudo-Riemannian manifold. And you can go on and put in things with all sorts of weird names, but they're all fundamentally the same kind of thing. Things that can be described purely abstractly with mathematical symbols and no human sort of baggage. And if you look at math that way, at math space in that way, that there's this very disturbing question, which is, why would, in Stephen Hawking's words, Stephen asked, why would God breathe fire into one of these equations and make a universe for them to describe and not others? Or like, what breaks the symmetry? Why is this particular one that's supposed to describe our world different from all the others? So the level 4 multiverse comes from this very radical conjecture that actually there is none of that metaphysics. There is no special fire breathing needed or whatever. All of these mathematical objects exist in exactly the same sort of way. And we just happen to be living in one of them. One of them that's complex enough that parts of it can feel subjectively aware of what they're going on, what's going on there, and sort of studying physics. Or to just break it down to plain English, what it's really saying is that we live in a mathematical structure, a mathematical object, which is something which has only mathematical properties. And here, I mean, you have to stop and say, well, that sounds completely nutty, right? What do I mean? You see the moose here?
We have a moose on the table.
Yeah, I was given it as a gift today.
Not a true moose.
What do I mean? This has only mathematical properties. Look at
it's made of cloth. It has colorful garb.
It's squishy, a little bit blue, and moose-like. Those properties I just described don't sound very mathematical at all, right? But when we look at it, Sean, through our physics eyes, we see that it's actually a blob of quarks and electrons. And what properties does an electron actually have? It has the property -1, 1/2, 1, and so on. And we physicists have made up these nerdy names for these properties, like electric charge, spin, lepton number. But it's just we humans who invented that language of calling them that. They are really just numbers. And you know as well as I do that the only difference between an electron and a top quark is what numbers its properties are. Mm-hmm. We have not discovered any other properties that they actually have. So that's the stuff in space. All the different particles in the Standard Model that you've written so much nice stuff about in your books are all described by sets of numbers. What about the space that they're in? Like, what properties does space have? I think I actually have your old nerdy, non-popular gravity.
My unpopular book, yes.
Space has, for example, the property 3. That's a number, and we have a nerdy name for that too. We call it the dimensionality of space. It's the maximum number of fingers I can put in space that are all perpendicular to each other. But it's the name dimensionality is just a human language thing. The property is 3. We also discovered that it has some other properties like curvature and topology that Einstein was interested in. But those are all mathematical properties too. And as far as we know today in physics, we have never discovered any properties of either space or the stuff in space yet that are actually non-mathematical. And then it starts to feel a little bit less insane that maybe we are living in a mathematical object. It's not so different from if you were a character living in a video game and you started to analyze how your world worked. You would secretly be discovering just the mathematical workings of the code, right?
Yeah, that's an intelligently designed environment, but yes.
It is, yep. I mean, I guess we can talk about the probability that we are living in a simulation
too, yeah.
also later. But if that is in fact the case, that we're living in a mathematical object, then what about the other mathematical objects that happen to also be well-defined? Why should we get on our high horses and say they can't exist as much as ours can? Maybe they're mostly stillborn because they're not complicated enough or whatnot. But you could say the same thing even about those other less controversial kinds of universe. Anyway, so that's the level 4 multiverse in a nutshell. It's simply it's math space of all mathematical objects that exist. And if this is true, the first prediction it makes is that all the properties of our universe, even the ones we haven't yet been able to understand, to do with intelligence and consciousness, for example, should ultimately also succumb to mathematical description.
But just to be clear, maybe it sneaked under the radar there. We can imagine the space of all mathematical structures, but you're making the extra statement that they're all equally real and we just live in one of them. Is that fair?
That's right.
That's the level 4 multiverse.
That's right. I really want to strip out as much human baggage as possible from this. And saying that something is real or not, like what does that even mean?
I think it means something.
About it. Well, it means something if you have this sort of very pagan kind of idea that this moose is real because it's made of stuff that's real, right? But then we come and look as physicists again, and just made of all these. The stuff is just these elementary particles, and what are their properties? They're all mathematical. So what is there here really beyond all these mathematical properties? I've yet to be convinced. I have a lot of. Usually, when people start trying to persuade me of things beyond that, it starts to feel very much like some sort of new agey thing that they just want there to be something fluffy and fuzzy and non-mathematical because they don't think mathematics is cool enough, or they say things like, "Oh, I can't believe it's just mathematics." I object to that derogatory use of the word "just."
Sure, I will definitely go along with that, but I do want to distinguish. I think maybe I should phrase it as a question. Can we sensibly distinguish between the idea that our universe is just a mathematical structure and that all mathematical structures are equally real, no matter what you might mean by the word real, but at least there's no difference in the level of reality between ours and others. Otherwise, it's not really a multiverse.
You're right. There are two separate questions there. First of all, does our universe have some non-mathematical properties or not? We don't know yet. If you had gone back 400 years and had Galileo on your podcast, then it would have seemed like, duh, of course it has non-mathematical properties, like, because the only stuff that we could even predict at all with physics was motion. Galileo could throw a hazelnut and a grape and he could tell you that they're going to move in this parabola shape, y equals x squared. But he couldn't tell you why the grape was green and the hazelnut was brown because that seemed non-mathematical. He couldn't predict why the grape was soft and the hazelnut was hard because that seemed non-mathematical. It was to do with the mysterious nature of stuff, right? But then we got Maxwell's equations, which helped us understand light and colors. And even that part of reality succumbed to the mathematical description. And then we got quantum mechanics, which explains now why the grape is soft and the hazelnut is hard. And we've gone from having a situation where the whole world seemed just mostly magical and the only thing we could predict about it was motion, mathematically, to a situation where we can actually apply math to almost everything except maybe intelligence and consciousness. They're the final holdouts.
Well, I did have a podcast interview with Philip Goff, who is a panpsychist, and the name of his book was literally Galileo's Error, because he says that Galileo made an error in making things too mathematical. Now, we'll plug your book, The Mathematical Universe, which says the opposite. So people can buy both books and decide which one is more persuasive.
I changed the title in the last second from The Mathematical Universe to Our Mathematical Universe because I thought saying the would be very arrogant. It's like when you say the solar system, it sort of implies that we're the only one, right?
That's true.
Whereas if we think seriously that there could be other universes, this is ours.
Okay, but wait, we got distracted because you were making the sales pitch for something I already agree with, namely that our universe is mathematical. But what about the others?
Yes.
The reality level of the others.
How do you make this jump from saying there's one mathematical structure which happens to be existing also physically? That's this one. How do you then get to the much stronger conclusion that all the other mathematical ones also have a physical existence? So the first part, I call it the mathematical universe hypothesis, which is that our external reality out there, which I believe exists and will continue to exist even if we all died, that it is purely mathematical. And I call that the external reality hypothesis, that it exists. And then I have an argument for why it should be mathematical. But then there's a separate logical step, which you raise here. How do you get from that to the idea that actually all the other ones also exist? I probably shouldn't bore you with getting into that too much in this podcast. But what I argue in the book is you basically just have to add a whole. You can take some mathematical structure and just study it very carefully. What are all the properties that it has, right? Mm-hmm. And you can say this here is this thing. It's going to be self-aware. It has information processing like this. And if you're really smart and can figure out how AI works and consciousness and whatever, you could figure out even how the parts, some self-aware parts of this will subjectively experience themselves in there. And you might find one that looks just like ours. You might find some other ones. And then you come to this question now, if you're going to claim that this one here that corresponds to our universe exists physically also, and some other one doesn't, what do you actually mean by that? You're positing that there is some additional property that this has, which has nothing to do with the math, which is whether it exists physically or not somehow. But this is nowhere to be seen in the math. Right? It's a little bit like if someone you try to convince somebody that they have a soul, and they ask you, okay, does my soul weigh anything? And you, no. Can I measure its existence with these particle detectors? And you say no. And then they ask you, well, does the soul actually push my particles around and make me act differently somehow? And you're like, no. The soul has no effect at all on your particles, but it still exists. Right? Then wouldn't you say that you're making yourself a little bit vulnerable to Occam's razor? They could just say, I'm going to take everything you say, Sean, and just shave off the soul part because it doesn't have any additional explanatory value. I feel that just as someone might say that the soul there is like a little fairy dust that's been sprinkled on, but it doesn't really add anything explanatory. You could say the same thing about this idea that there's this extra magical property that a mathematical structure has called physical existence, but it doesn't have any effect on the mathematical relations that hold within it at all. And I can ask you, well, does that say anything about whether these two lines that are parallel are going to cross or not? And you say no. Does it have any effect on whether this self-aware object here is going to experience X or Y? And you're like, no. So it has no effect on any of the relations in there. That to me also is just as vulnerable to Occam's razor now, because it sounds like just philosophical BS, really, that has no consequences on any of the mathematical relations. And I would just assume, my guess is that it is just philosophical hogwash, and we should just accept the fact that regardless of whether something is a computer simulation or exists in some other way, all that matters about it is how what the relations are within it. That's what determines how it feels like to live in it. So there you have it, basically, a mathematical universe. And if you this leads very naturally into this question about whether we're living in a computer simulation also, because if you and I were arguing about whether we're in a simulation right now, right? And I'm like, no, there's no way, because this moose here, it's real.
Feels real, right?
It's physically real. And if we were in a computer simulation, the moose would not feel real. Like, how would you respond to my argument?
Yeah, that's a dopey argument, right?
I'm claiming that my argument is basically the same argument. That the way I experience the moose, Max, the computer game character here, has only to do with what the mathematical properties are of this computer simulation. Has nothing to do with whether it's being simulated on a Mac or a Windows machine or a Unix machine. It's just internal mathematical properties of this simulation that matter. I would say it's the same with the mathematical structure. All that matters are the relations in it, not whether some philosopher says that it's sort of made of real stuff or not.
So I certainly forget whether I buy it or not. That's irrelevant. But I understand the argument that it is absolutely a simpler idea to imagine that all mathematical structures exist than to imagine that we can conceive of all mathematical structures and we're one of them. There's a lot of information that goes into pinpointing which one we are, right? Which you're happy to get rid of. But then I think, and at the risk of getting a little bit technical here, it would seem that to make sense of this idea, you need some kind of way of comparing the different kinds of universes, the different kinds of mathematical structures. There are so many that look like this, so many that look like that. And I would also think that once you had that way of comparing, there's far more universes that kind of look like ours and then explode into chaos a second later, right? Than to keep up this very, very specific obeyance to the laws of physics. So doesn't your theory make a prediction that we're all going to cease to exist within a nanosecond?
As the Baltimore brain would? That's a very good question. I think the answer is no, for reasons I'll explain in a sec. But first of all, I'm totally open to the possibility that this idea is wrong. And I'm very interested in testing it in various ways. I think, to me, this idea is more of an inspiration for a research program to try to find more mathematical regularities, because we're never going to find any if we don't look for them, right? If we say consciousness is off limits because it's not mathematical, we're not going to discover any equations that might actually help explain it, say. In terms of your question about whether the most generic thing we should expect is just random weird stuff taking place, I have a suspicion that just like in cosmology, when we study infinite spaces and so on, we stress out a lot about the so-called measure problem. To what, which things exist sort of more often or to a greater extent than others. That there is something very similar to that unsolved problem here. And I think it's going to have a lot to do with complexity. In some sense, maybe very simple mathematical structures that are simple to describe get more weight. If you were just randomly bored and simulated different universes on your future supercomputer, the simpler ones would get a lot more attention than the more complicated ones because they could be evaluated much faster, right? And I sometimes wonder, this is a very quarter-baked idea, if the reason why our universe seems so remarkably simple when you look at the fundamental laws might have to do with that simplicity is very much favored. And if that's true, then we shouldn't just expect that the past has been simple, but we should also expect that the future should be kind of simple, because it's much more complicated to define a simulation algorithm or a mathematical structure where suddenly a pink giraffe appears randomly in my office, right? Than to just specify the standard model that we have today, where that's probably not going to happen.
I'm worried that as far as that goes, yes, if there were an additional principle that would somehow favor simplicity, you might be able to account for our universe. It's simple enough. It's a little complicated, but it's simple enough. Mm-hmm. You might hope for that. But I do worry that that's another metaphysical principle that you were just trying to avoid mere moments ago. You've gone away from the pure, pristine beauty of everything mathematical exists. That's all there is to it.
So first of all, I try to be very humble. So I'm not saying I believe that
No,
any
of
of
course,
these
that's
universes
fine.
exist. My job as a scientist isn't to believe stuff. I'm happy to make bets, though.
One has credences. One's a good Bayesian.
Yeah, and second, whether you feel that something is frivolous and full of extra assumptions or complicated or not depends a lot on what you mean by simple. Many people criticize any kind of parallel universe as being wasteful because they waste a lot of atoms. Like, I don't buy this idea that space is infinite or bigger than we can see because, oh my gosh, there's all these extra atoms. A different perspective is that simplicity should be measured by how simple the mathematical equations are. It turns out it's much easier to write down some physics equations that actually give us this really big space than to write inflation that makes a really small space, which is exactly as big as we can see, and then magically stops.
Yeah.
And it's the same thing we've seen in quantum mechanics, where it turns out to be much easier to have the Schrödinger equation that just has all these parallel worlds than to add in a bunch of extra stuff that's supposed to get rid of all the parallel worlds. And I feel in the same sense that the level 4 multiverse is actually simpler. We were joking about a t-shirt earlier, where you write down the theory of everything, right? So if you did that 2,000 years ago, oh boy, would you have to have a small font. You'd have to say, well, we live in a solar system as a blah, 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 and then this is what the garlic looks like, and this is what a watermelon, and this, copper, and periodic table. Well, if you just fast forward a little bit, they wouldn't have to specify the whole periodic table. They could just write down this equation for QCD, for quantum chromodynamics, and 3 numbers, and from them you can compute, in principle, the whole periodic table and books full of numbers about how atoms shine light in different colors and stuff. So more simplicity now. And I think by going to the level 2 multiverse, you don't even have to write down numbers like that proton-electron mass ratio of 1836, because that doesn't have to go on the t-shirt. That now it's your address. You find out if you want to know where you're living, you go measure that, and now you know what part of the level 2 multiverse you're in. At the level 4 multiverse economizes even more, because without it, you have to put on your t-shirt at least the equations for string theory or loop quantum gravity or whatever the correct quantum gravity theory is, right? You have to put that. In the level 4 multiverse, you can just wear a black t-shirt with nothing on it, because all of the mathematical structures exist, which you can try to catalog with a future computer program, exist. And that's kind of all there's to it.
I mean, I don't want to dwell on this too much, but it sounds a lot to me like Borges' library, right? Like Borges said, what if there's this library that literally contains books with every possible sequence of symbols? And somewhere in that library are all the works of Shakespeare and the Bible, and for that matter, every book ever written in the future, right? The problem is finding them. The problem is that the card catalog is the same size as the library. Most of those books are utter nonsense.
Yeah, and there's another problem with it. There's really no structure in it. There's no sense in which simple books are more important than complicated books. So the average generic book is just pure garbage. What's so different about mathematical structures is it's actually very hard to write down a system of axioms and theorem-proving rules that are even consistent at all. So the great mathematician David Hilbert once said that mathematical existence is simply freedom from contradiction. And it turns out to be just really hard to do that. So there's, some people like to say that something exists if you kick it and it kicks back.
Yeah.
Mathematical structures are a lot like that. If Plato, for example, was really interested in regular 3D shapes, and he discovered that there are 5 of them. They're called the Platonic solids, the cube, the icosahedron, etc. Right? And no matter how hard he tried, he couldn't just make up a 6th one. There just isn't one. He could make up names for them, but he couldn't make up more. So in that sense, mathematics kind of kicks back. They discovered the dodecahedron made of 12 pentagons and thought that was so cool that they didn't tell anyone. They thought it had magic powers, and you see it sometimes in art museums in the corner of some paintings. Discovering that shape was a little bit like when we discovered the planet Neptune. It felt like it was out there all along, and now, we found it. So the math space is much more interesting than Borges' library, in the sense that There's a lot of stuff
More
in
structure.
it, but it's absolutely not the case that just everything exists. It's not like, some people sometimes criticize social sciences for being very loose and loosey-goosey about things. If you just take some random mathematical structure and just add one more axiom to it, often like pops the balloon and the whole thing just collapses to nothing.
So would it be, you're leaning on simplicity quite a bit. I mean, you've also alluded to the idea that everything that we do see in our physical universe is just running on some computer somewhere in super advanced civilization. Is that simpler or more complicated?
I would actually bet against the fact that we're living in a simulation, not because I think it's impossible, but because I think it's less likely. So Nick Bostrom, or Boström as we call him in Swedish, popularized this so-called simulation argument. And what he basically said was, we're building ever better computers. One day we'll be able to have much more simulated minds than real minds, so therefore we should expect ourselves to be a simulated mind. I claim that that argument is actually flawed in the last step. And you can see it sort of start falling apart already by just taking it one step further. Like, suppose you agree with it, so we're simulated. There is some sort of basement universe with actual physical stuff, but we're not in there. We're in one of their computer simulations. Nothing prevents us from making the same argument again. In our simulated world, we're going to have more simulated computers, and they're going to do doubly simulated minds, and they'll outnumber us. So therefore, we're doubly simulated. And now we can do it again. We're triply simulated. And now you're simulated 1 trillion times. Are you getting a sinking feeling at this point?
Well, I mean, go ahead. Finish the argument. Is it just that we should be infinitely simulated? Is that the argument?
That's what the simulation argument logically implies, that we're basically infinitely simulated, which already feels a little bit fishy. And I think
I had the flip side of that argument, which is that according to that logic, the large majority of beings should be in the lowest resolution simulations, right? Because they're just the easiest to make, and so they would win. But empirically, we don't see, I mean, it's easy for us to make simulations, and so we could easily have lower resolution than what we see around us. Therefore, there's some logical flaw.
I like that too. There was even an interesting paper a while back where they had tried to look for evidence that we're simulated by finding weird noise and things.
They didn't find any, by the way, for readers out there.
Yeah. But I think where the argument goes wrong is very interesting. What it's saying is you should have this basement reality. It has some laws of physics in it where there's real stuff. And in that basement reality, if you can there make the argument that most minds in there are going to be simulated, sure, now you are onto something. Maybe. But we don't know that we're in the basement reality, right? If we conclude in the end that we're simulated, then we have immediately violated that assumption. And we have no idea, in that case, what basement reality we're actually simulated in. So the thing that would matter, the only thing that could make this argument work is if you knew for sure that you were in the basement reality, so you can make some statements about what's actually probable.
Yeah. But just to be very clear,
you conclude,
you're totally on board with the idea that maybe not everyone listening is on board. I'm on your side here. Life in a simulation would be just as real in life as life in the basement reality, right? I mean, you could simulate things. There's no substrate dependence. The people in the simulation could, in principle, have all the hopes and dreams and consciousness that you and I have.
Mm-hmm. I want to be humble here. I mean, there are many people who think that there's something mysterious about intelligence, and think that it can only exist in biological organisms such as us that exist sort of in the basement reality. But I'm not very fond of that viewpoint. I call it carbon chauvinism. Mm-hmm. The idea that you can only be smart if you're made of carbon atoms. I think it's, in fact, exactly the opposite of carbon chauvinism that's giving us the whole AI revolution. The opposite of carbon chauvinism is the idea that intelligence and consciousness are all about information processing, and it just doesn't matter whether the information is processed by carbon atoms in neurons in brains or by silicon atoms in today's technology or some other kind of particles in tomorrow's technology. And if you accept that it's all about information processing, then of course an entity in a really good simulation with the right kind of information processing is going to feel the same way they would feel if that information processing happened on some other substrate, right? And just like they will have no idea of knowing whether they're simulated on a Mac or a Windows machine or a Linux machine, they will have no idea way to tell whether they're actually simulated at all or living in an actual physical universe that has those laws.
And so would you say, so not to put words in your mouth, tell me if this is accurate. It's possible, it's conceivable that we are living in somebody else's simulation. Among people who buy that, there's the response that, but I don't care. And there's a response that, but I think it's unlikely for the following logical reason. It sounds like you're saying you think it's unlikely, but you would be interested in caring if you thought that it was likely.
Oh, totally. I agree with all you said. I think we might be. I have not seen a compelling argument for why we are, and I think there's a little bit of experimental evidence against, since it just seems like the quality of this one is a bit higher than it would need to be. Although sometimes when I pay attention to politics, I take that back. I think the quality maybe isn't that high after all. But that aside, if you still have a lingering doubt that you are simulated, I mean, the advice is pretty clear. Just live a really interesting life so those running the simulation don't get bored and shut you down.
How do we know what's interesting to them? This is the question. Well, so let's flip it around.
Well, you seem to be doing it right since you haven't been turned off yet.
As far as I know. I mean, the thing about being in a simulation is they can always hit a save point and shut down the simulation and start you up years later. Who knows how many times that's happened in our lifetime, right?
Indeed.
The clock in our universe need not be the clock in their universe. This is where it gets scary. But let's turn it around. If the simulation theory is true, then there are super beings in the basement reality who have built a computer and are simulating us. And then
the intelligent design that you despise so much is true.
That's right, exactly. But then what about the other way around? What about us building simulations with AIs in them? I had Melanie Mitchell on the podcast recently, a bit of a skeptic about AI's ability to reach human levels of intelligence, at least near term, not in principle, but how close we are. What is your feeling to how close we are? Because this is kind of what you're doing these days, right? You're doing more AI than cosmology.
Yeah, my research group here at MIT, we've been doing AI research for the last bunch of years. And so if you look at my nerdy papers, they're published in AI journals and AI conferences.
And by the way, is that more a response to the state of cosmology or the state of AI or the state of Max?
That's a good question. I think it's a little bit of both. The first two, actually. I've ever since I was a teenager been just really fascinated by the biggest questions. The bigger, the better. And I remember thinking back then that the biggest mysteries of all were our universe out there and our universe in there in your head, right?
Yeah.
So I spent the first 25 years of my career on the outer universe. It was super exciting. And in recent years, I've just felt ever more intrigued by the second part, and I realized that not only that this pace is picking up so much that it's really fun now, but also that we physicists actually have a lot to contribute to that field in ways we can come back to. But to get me back on track, you asked a question before you asked my personal.
What is your statement? What is your feeling about the state of the progress?
Yeah. What's more interesting than what I think is what AI researchers have said across the world in recent surveys, which is that most of them guess AI will succeed within a matter of decades to get AGI, which is an acronym for Artificial General Intelligence, which just means AI that can do all intellectual tasks at least as well as us. Superintelligence is something way beyond that in turn. Is that actually gonna happen? There's of course a lot of people who dismiss it and say, forget about it, it's not gonna happen ever because it's impossible, because intelligence is something mysterious somehow, and all those people who say it's about information are barking up the wrong tree. Maybe they're right. I would guess that they're wrong. And just as in any field, you have a genuine scientific controversy about how fast or slow things are going to be. But I think it would be a mistake to dismiss it being that it's possible. Sure, we have many embarrassing examples of scientists being over optimistic of how quickly things are going to happen. Remember when you and I were both starting grad school, fusion was 40 years away.
Oh, yeah.
It's still 40 years away.
But on the other hand, we thought we'd never know the density of the universe.
Yeah, and now we know.
Hard to predict the future.
1.68 times 0.7 squared times 10 to the minus 26 kilograms per square meter. And we've gone for about the age of our universe from arguing whether it's 10 or 20 billion years to arguing about whether it's 13.7 or 13.8. So that's progress. And so it's very dangerous to say something is impossible when you're on a planet with a lot of smart, motivated people. For example, Ernest Rutherford, right, one of your physics heroes, grandfather of nuclear physics, famously said that this idea of getting nuclear energy, moonshine. Do you know how long it took from when he said that in a lecture in London until Leo Szilard invented the neutron chain reaction?
It couldn't have been that long. A decade?
Less than 24 hours. Actually.
Oh, okay.
So we have to be, the bottom line, I think, is you just have to have an open mind.
Yeah.
Could happen in decades, could be a bit sooner, could be take much longer. But I think if it's a few decades away, that already makes it arguably even more urgent than thinking about climate change and your retirement, because this is going to be a much bigger deal, obviously, if it happens. If some human you don't like very much, think about your least favorite politician or unscrupulous business tycoon has this and can use it to take control over Earth and impose what they think is cool on you, you might not be so stoked about that, right? Alternatively...
So, sorry, I don't want that to go by too quickly for the people out there. I mean, this is the worry of artificial general intelligence, that it will give either the AI itself or the people controlling that AI some version of superpowers that will be hard to control for the rest of us, and therefore we should worry a lot about AI gone wrong.
That's right. And I think the reason I decided to start my AI book, Life 3.0, with a little fiction story, was exactly because of this. Hollywood gets its worried always about the wrong things. It's always robots because they have to have something they can film because it's a visual medium. Intelligence itself can confer great power. Like, why is it that humans have more power on this planet than tigers? Is it because we have sharper claws or bigger biceps? No, it's because we're smarter, right? And that means, of course, that if someone can amplify their intelligence with vastly stronger AI, it can confer enormous power on them. They can pretty quickly outsmart others on the stock market and out-patent them and out-argue them on your blog and whatever, and have a lot of influence. And is that good or bad? Well, that entirely depends on how it's controlled and with what goals. I think, like any technology, of course, AI will be a double-edged sword. People sometimes ask me if I'm against AI or for it. I usually counter by asking them if they're about fire, like are they against it or for it? Like, duh, it's a dumb question. The interesting question is, what can you do to get the upside of fire but not the downside? Turns out there's a lot you can do. That's why we have fire extinguishers and fire escapes, and we teach our kids to not, and blah, 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 That to me is the most interesting question, important question of our time, I think. How are we going to harness this technology to make sure it gets used to cure cancer and lift people out of poverty and help life flourish like never before? Hopefully not just during the next election cycle, but for billions of years, and maybe not just on this planet, but throughout much of our universe. Right? It could be awesome. On the other hand, you don't have to think too long to envision scenarios where it's not so great. For starters, if you just, again, envision your least favorite politician using it to impose their will on everybody. You don't even have to get to things where the AI itself sort of breaks out and takes over. Just, there are a lot of people you probably wouldn't want to control you.
So I had the following worry, which I haven't really put in front of AI experts such as yourself yet. If it's going to be AI at all, it is going to need the ability to learn and therefore to change itself. So isn't there an intrinsic issue with the idea of controlling it? Like, you can tell it not to do something, but if it decides to change its mind, what are we going to do about it?
This is very active research in AI today, how to actually take these deep learning systems which have learned stuff and where you don't really understand in detail how they work, and seeing, is there some way nonetheless, by having better architectures, where you can actually prove that they're always going to do certain things, or it breaks into 3 different nerd problems, which are all unsolved, but which we all also face as parents, I would say. We want the AI first to understand our goals, and then adopt our goals, and then retain them. You know, our little babies, first they're too dumb to understand most of our goals. And then they're teenagers and don't want to adopt our goals. But fortunately, our kids spend several years in this in-between period where they're smart enough to understand our goals and hopefully malleable enough that we have a little chance at persuading them.
They're weak enough that we can control them, yeah.
Yeah, and that's what that's what parenting is fundamentally about. But even if we succeed in getting AI to understand our goals and adopt them, how can we make sure if they keep getting smarter that they retain them? You know, like Philip and Alexander, you can see them on those pictures there when they were still small enough that they thought Lego was the coolest thing. That was a big priority for them. Now all those Legos are gathering dust in the basement because they're 18 and 20. Yeah. If we create powerful AI that has this goal to really take care and protect humanity, we don't want it to become as bored with that as they got with Legos, right? Yeah. So you would also like to have some sort of recursive algorithm where you're guaranteed that there are certain goals it's always going to retain. And the interesting news here is that there's been a lot of technical progress, actually. We put a big effort in 5 years ago with this Future Life Institute to bring together AI researchers and others at conferences to talk about these technical questions. And with the goal of mainstreaming that research so more of it would happen. And it's been very exciting to see, actually, how much is taking place. Stuart Russell, for example, famous AI professor, just has a new book out called Human Compatible, where he actually doesn't just, once again, lay out these challenges, but actually proposes what he considers a cool solution. The good news is we still have time. Maybe we have, a few decades to get this right. My message is, on one hand, don't freak out and panic, but on the other hand, work hard on these technical questions now, so we can get the solutions when we need them, because it might take decades, right? Rather than start working on them the night before someone switches on an AGI.
Well, okay, we're running low on time, but I do want to give this leads very well into you giving a little sales pitch for the work that you're doing now that I heard you talk about at the most recent Foundational Questions Institute, where you're training AIs to be theoretical physicists, right? To find the laws of nature by looking at big data sets, not just find patterns, but really find quantitative laws. Tell us what that project is and how it's going.
So we call it, my grad students and I, the Intelligible Intelligence Project. So, as you know, most of the progress in AI these days has moved away from this old paradigm where a human programs in the intelligence to a new paradigm where the computer just learns it itself, usually better, at the cost of you having no clue how the darn thing works.
He just knows better than you.
And that's fine if the stakes are very small. But like if chess. This is the thing flying your airplane or your Boeing 737 MAX or controlling the nuclear arsenal or something, you'd like to have a higher bar on really trusting the thing than just some dude telling you that I trained this on 15 terabytes of data and it worked every time. And I'm quite convinced, actually, that we can make a lot of progress. I think there's a common misconception, almost like people almost worship the mysteriousness of neural nets and say part of the magic of them, that makes them so powerful, is that they're inscrutable. I think that's not true. I think the power of them doesn't come from their inscrutability, but from their, differentiability in nerd speak, but in plain English, from the fact that they're basically a black box with a lot of knobs that you can continually tune until they work really, really great. Mm-hmm. So they can learn for themselves from data. And what I would really like to see is where we combine the best aspect of this new paradigm of machine learning with the old school thing, with little programs that are human understandable and simple. We humans actually know it's possible because we do it in our brains, right? If someone teaches you to play baseball or whatever, you get pretty good at it by training your neural network. But then if someone asks you, how does a ball move exactly? You can explain in English. You can say, it moves in this shape called a parabola. Here's the equation for it.
Yeah.
And if we can do it, and if you don't think that intelligence is something mysterious, limited to bioorganisms, there's no reason we couldn't also develop AI tools that can do the same. We can first use this power of deep learning to figure out how to do stuff in an obscure, unintelligible way. And then rather than just stop at that point, do some additional things, try to simplify down to something that can be explained and understood. As you mentioned, we've had some progress doing this with simple physics problems. And if we could make more progress, I think there's a real hope here that we can get systems that we trust better. Trust for the really simple reason that we actually can understand how they're working. You know, the real threat from AI systems today is not that they're going to turn evil like in some lousy Hollywood movie, but that they just turn very competent and accomplish things we didn't want them to accomplish because we hadn't fully understood them. Like, Boeing put this very simple system into their 737 MAX things, and they hadn't understood how it worked. It didn't work so well for them. Knight Capital had this trading algorithm that they hadn't fully understood, and it lost them $10 million a minute. It kept going for 44 minutes until someone was like, oh, shut this damn thing off. So we're putting AI in charge of ever more decisions and infrastructure that just affects people's lives. And I think we should and can raise the bar and making sure that these are things we can actually understand. And since we're running out of time, can I say something a little bit optimistic?
Please.
Since you've been
I'd like to
quizzing
end
me
always on an optimistic note.
downsides. The risks get so much airtime because of Hollywood movies and so on. And yes, there are very serious risks.
I mean, you founded something called the Future of Life Institute.
Which sounds a little bit hopeful. Yeah.
I don't know.
But of course there are.
It begs the question of whether or not life is something that we might not have a future for.
Well, and of course, if we create something more intelligent than us, you don't have to think very long about it until you realize that, someone we don't like could use it to do all sorts of bad things. Of course, things could go to hell in a handbasket. But that's just the nature of any powerful technology, right? The interesting question for me is not to quibble about whether you should worry or not. The interesting question is, what can we do right now to maximize the chances that this goes well? First of all, what we have to do is some nerdy work that I discussed. For example, try to build systems that we can trust because we can actually understand them better. Second, we have to really have a conversation about what kind of future we actually want. We're here in my office at MIT, right? And at this very table, I often have students coming in for career advice. And I always start by asking them, where do you want to be in the future? And if she looks at me and all she can say is, oh, maybe I'll get murdered. Maybe I'll get cancer. Terrible strategy for career planning, right? I want her to come in with her eyes shining and saying, Max, this is where I want to be. And then we can talk about strategies for actually getting there and all the pitfalls that she should avoid, right? And that's what we should do as a species also. But are we? No, we're doing exactly the opposite. We're doing precisely this sort of silly thing that's fortunately, I hope she won't do. We go to the movies and watch sci-fi about the future, and it's almost always dystopian, right? Which makes us paralyzed with fear, basically. And we really need to have a serious conversation about what kind of future, high-tech future, are we truly excited about?
We also want to not get murdered along the way.
Of course. But it has to start with a shared positive vision. That's so cool that you can get people in China and in Russia and in Kansas and in LA all on board about it, saying this is a future for humanity that we all agree we're all going to be much better off. We would like this to happen. That fosters collaboration. And that's the time to start making lists of the things that can go wrong that you have to then make sure you avoid. If you can't start by even giving the positive vision, they're not going to want. If you're going to feel it's a waste of time talking about those things, right? In 1945, people in Europe, where I was born, looked at each other and said, "Oops, we screwed up again," and something really remarkable happened. Some people decided to see if they could come up with a really positive vision for a change, for how they were going to use this ever improving tech for not just making ever more powerful weapons, but maybe create a society that was awesome, where everybody could have free healthcare, free college education, free pensions, and a society where everybody was better off. And I'm pretty sure that back in those days, they got poo-pooed a lot, and go smoke some weed, hug a tree, it's never going to work. But the positive vision was compelling enough and realistic enough that they got enough support that it started to happen in countries like Sweden, England, Germany, and soon and by now it's happened in all rich industrial countries except the one that we're in. And that's the power of a positive vision, right? And I would like to see a new vision, which is much more ambitious, that's powered by AI, for how we can have a truly awesome future for everybody on the planet, where we amplify our own intelligence with artificial intelligence to solve all the problems that we're stumped on now, and we think hard about also how we're going to not just make the tech, but how we're going to make sure that it's deployed to help everybody, rather than just to help me, Max, who owns all the tech, to take over and screw all the rest of you. If we can have such a shared vision, then I think it's really much, much more likely that we're going to get it.
All right. I love it. I love the optimistic way to end. I do want to foresee the future where you and your students build little AI agents which get conscious enough that they can deny that we exist. They refuse to believe they live in a simulation.
Would you invite them on your podcast then?
I would. I would love to have that. All right. Max Tegmark, thanks so much for being on the podcast.
Thank you.